These particular videos in this class are about a branch of physics called mechanics. And mechanics sort of refers to the idea of analyzing and discussing motion. Motion of objects, say everyday objects that we're used to dealing with, like cars and balls and scooters and bicycles, and even things like rocket ships and planets going around one another. So it turns out then, if you want to have a mathematical foundation to describe the mechanics, which is a very large part of what we're going to be doing in this class here, you need to get some variables on these objects so you can sort of track them. So for instance, here's a car here I've sort of drawn, which might be going this way down the road. I'll draw some wind behind it and stuff, sort of buzzing along there. The variables you'd attach to a car like this would be, say, something like x, which would be its position, say, from a stop sign or your house or something. It would have some speed v, and it would have some acceleration a. So it turns out those three variables are three variables that are attached to this thing that's moving, and they can be used to fully describe, predict, and analyze its motion in many different circumstances here. X, v, and a, its position, its speed, and acceleration. Those three things are attached to any object that moves, and manipulating them is sort of a key part of the class. Now, it's very nice for the car to be moving along the road, but then say, what if you have a ball that's dropping like this? Here's a building like this, and say there's a ball right here, and the ball's been thrown off the building, and it's dropping like that. What variables would you give it? Well, x, v, and a would work, but to make it a little bit more convenient and intuitive here, we instead call it y, v, and a. Now, the reason why we choose x for the car and y for the building is because all through grade school and so on, we're used to the Cartesian coordinate system where the horizontal axis is labeled x and the vertical axis is labeled y. So we typically associate things moving horizontally with the x-axis. That's why I gave x to the car, and things moving vertically with the y-axis. That's why I gave the ball the y-axis. But if we're going to get really particular about the motion and the variables and so on, if this is going to be x, maybe I should even label the v sub x, just to say, hey, it's an x velocity, a velocity that exists along the horizontal, the way that car probably has. And maybe I should even label the a sub x to say, hey, this is an acceleration of the car, a horizontal acceleration along the x-axis. Likewise, here's the y, the v, the a. Maybe I should label this y, and this not just v, maybe v sub y, and this not just a, maybe a sub y, like that. So this would be a very nice, complete set of the three variables that are attached to this object. These would be the three variables that are attached to this object. And again, my claim is that these three variables will always be attached to anything that moves, the speed, the position, and the acceleration, and those are the ones that you need to make analyses now. The analysis typically happens of these things using three equations. The first equation, say, for the x-axis then, would be x is equal to x0 plus v0 delta t plus 1/2 a delta t squared. That's for the position equation. The other one is the velocity equation. v0 plus a delta t, like that. So we have two equations, and these two equations, along with the parameters that we're setting for the car, these can be used to say all kinds of things about the car's motion. Now, we'll get more careful once again. If this is all x-directed motion here, we could get in and just be more organized with our labeling. This isn't absolutely necessary, but it's not a bad idea here. This could be v0 x along the x-axis. This could be an ax right here. This could be a v0 x there and an ax right there. Just say, hey, look, all my v's and all my a's are pertaining to the x-axis like this car would require, so maybe I should be very careful and organized with my notation so there isn't any confusion. Because there's the same two set of equations that would be adapted, say, for the ball or something moving along the y-axis then. I would have y equal to y0 plus v0 y delta t plus 1/2 ay delta t squared. There's the equation that would sort of work on the y coordinate. And likewise, I would have a v here that would be, say, v0y plus ay times delta t. That would be the equation that would predict, track, and hold all the information for the three variables of the ball, the position, the speed, and the acceleration. Now, I just realized as I was drawing this, we could dress this up even more here. The v up here should probably say vx because that's in the x, and the v here should probably say vy to get it in the y there. But here's a complete set of equations, and notice they aren't different. They've just been readapted to themselves here. It's always something like position is equal to initial position plus initial velocity times delta t plus 1/2 times acceleration times delta t squared. But we've adapted the equation symbolically to reflect motion either along the x or y axis, because we might need both in the problem. Maybe the car's going to be going horizontally, but it's going to fall off a cliff, in which case we need some vertical analysis of it, and it's best to keep the symbols nice and organized. And one thing I also want to caution you about here, about these equations here, I think it's wrong and not really the right understanding to write something like this: x equals to x0 plus v0t plus 1/2 AT squared. This format isn't so appealing to me anyway because of the way this t is drawn in here. It's just not clear what time are we talking about here. Is it reference to 0 or 5 minutes or an hour ago or something? I think we much prefer to put the delta t in there to indicate that the variables are all tied together over some time interval. Like if the car was here and then a few minutes later maybe it traveled down the road until it was right here, something like that. There's the car. We could say something like a little delta t of time went by, and that's what these equations sort of predict. But it's not so clear what we're measuring time with respect to when we just put a t in there, the way some textbooks and maybe other venues of physics might do it. So we like to stick with the delta t's, although the equations are the same. So those are the three variables: position, velocity, and acceleration. They've been adapted to the x and y coordinates as we'll need all through the course. We're basing on the familiar Cartesian coordinate system, and there you have it.